Hey guys, it's Sven. Today I'm going to implement the transformation layer with you. This is crucial to cut down three-dimensional inputs to one-dimensional outputs or inputs. This is, for example, needed if we, let's say, have a layer type that comes later, the convolution, that needs like 3 or 2 dimensions, but our dense layer can only handle with one-dimensional inputs. So for that, we need to cut that down. There are no weights in that layer. It's like only going from 3-dimensional into 1-dimensional, and that's like only mapping 3D into 1D, and that's actually pretty simple. So let's go ahead and do that. I'm going to create a new layer. I'm going to call it transformation layer. On the web, there are like different names for that. I've seen flattering layer somewhere, but I'm going to call it transformation layer. So this extends the layer. And as I said, there are no weights inside. Well, I'm going to need the constructor. And there's also no we can't define the output depth yet. It's like only depending on the input. And this is like, we're not doing that one yet. So let's take the empty constructor and implement some methods. On build is, we don't need that. We have no weights. We have nothing in there. What we need is we need to calculate the output dimensions. And this is pretty simple. So we have this dot output depth and output width is equal to 1. So there's like there are no, we are not going into the depth or width. We're just going into the height. That's like the third index of our arrays. So this dot output depth and output width is 1. And this dot output height is equal to the amount of neons in the input, and this is like this dot input height times this dot input width times this dot input depth. That's it for the output dimensions. There's also no weights update, so we can ignore that for now. The calculate is, we are going to map one 3-dimensional input to one 1-dimensional output, and for that I'm going to make a new method. I'm going to call it map. I'm going to make it private, I think, and it returns the index in the output layer, in the output height, or like just the index, private int index of input, and it takes in the x, the y, and the z. Or let's say the depth, the width, and the height. And how we're going to calculate it is the following. This doesn't really matter how you're really going to calculate this, but this is like a method that I use, and I'm going to return the the depth times this dot input width times input height. This is like the amount of neons, like if you want to think about this, how this works, the amount of neons that we have passed when we increase the depth by 1. So like if you think about that 3-dimensional, we have passed like the input width and input height if we increase the depth by 1. Also, we are going to add the width times this dot input height, it should be, I think, and we are going to add the height eventually. This will lead to any kind of combination in here will have a specific index. So in the calculate method, I'm going to do what we always did before. I'm going to make I'm going to make 3 loops, and I'm going to iterate through the input, and I'm going to map it to the output. So for int I equals 0, I smaller than this dot input depth I plus plus. Then for int j equals 0, j smaller than this dot input width and j plus plus. And for int k equals 0, k smaller than this dot input height this time, and k plus plus. And then it's like there's no calculations really happening. We're just like mapping the 3 dimensions to 1 dimensions. So this dot output values at a 0, 0, and the map function. So index, I should probably call it map. Oh no, I'm going to stick with index of output. Index of output of I, j, k is equal to the input at that specific neon, or that specific 3-dimensional neon. So this dot didn't I have, okay, wait, this dot probably previous layer got get output values at I, J, K. I need to check if there's a different way of getting the input. Give me a second. I'm kind of confused that I haven't done that. No, I've done it the same in here, okay. Well, I'll just stick with that then. So, yeah, we need to feed forward the output values, but also the derivative. This is really important. If you don't do that, at this point you will get stuck and everything might break apart, because the output derivative of this layer at the moment is 0. So when we update the weights of the next layer, we're going to end up with no update, because we need to multiply it by the derivative at some point. And yeah, this is just breaking everything if we forget this. So output values, derivative values is equal to the get output derivative values, like this. This is, I guess, pretty easy. And like the calculate signal errors of the previous layer is exactly the same. We're just going to feed our signal errors to the previous layer, and we're going to iterate through the output through the input, or like the output of the previous layer, and we are going to set the errors of this previous layer, get pref layer dot output error values at ijk, no, not like this, ijk is equal to this dot, come on, this dot output error values at 0, 0. Then we need to use the index of input function again, and this is like I, J, K in that order. And I think this is already it for the transformation layer. And we can check if this works as expected by just like making a little example, public static void main string args. Then I'm going to make a new network. Therefore, I need a network builder is equal to a new network builder. My input is going to be like, let's say 1, 3, and 3. That's like 2-dimensional, but it's pretty much 3-dimensional. Then I'm going to builder.add new transformation layer. And in theory, this should give us a 1-dimensional output with 9 neurons, because we have 3 times 3 input neurons, and the output should have 9 neurons. So there are no parameters in there. Then I'm going to builder dot network. Why can't I like this? Yeah, network is builder dot build network, and net dot or system dot out dot println net dot calculate. Okay, then I need to create a new double array. I hate doing this, so I need 1, 2, 3. I'm going to 1, 2, 3. Why does this not work? I have the first dimension. Oh, okay. Let me think about that. No, actually, that should work. No, that shouldn't. Gosh, come on. It's a while since I've done this. Okay, I need. Why doesn't this work? Like, why can't I just write numbers in there? Shouldn't I be able to do that? Wait. Let me quickly do something new. Double. If I do this, I'm going to simply have it like that, and then like that, and then like that. Okay, sounds good. But oh, okay, I know what's the problem. I need one more brace like that, and this comes in there. So 1, 2, 3, then let's say 4, 5, 6, and then 7, 8, 9. This isn't pretty right now, but I will stick with that. Maybe like this. Okay, and let's not print line that. Let's use the layer function. We have layer dot print array, and in theory, this should hopefully print like a one-dimensional array with these numbers. I'm not sure about the order, but the order doesn't matter. So if it's like 1, 4, 7, that's still fine. But there's a problem somewhere. Oh, okay, yeah, that's because I just deleted that before I made this video. So it should still work, I think. And yeah, it actually works as expected. So the numbers are in one array, and we can even like do it with higher dimensional things. If I, for example, go in here and make a, I can make, for example, 3 dimensions right now, and this should still work, I hope. So I'm going to copy this one and add it in here like this. And I hope I didn't mess up anything. I probably did. No, I did. So yeah, that's like 27 outputs, and it's like still in the correct order. But yeah, that's like how the transformation layer works, and it's like the part between the convolution that comes later and the dense layer. And in the next video, I'm going to use this to make 2-dimensional or 3-dimensional MNIST data sets and still use the same network that we had before. So see you in the next video.